Particle equilibrium in 3 dimensions is not really much more complicated than that in 2 dimensions. We now have 3 mutually orthogonal directions instead of 2, so we have 3 scalar component equations. Particle support reactions in 3D are a straightforward extension of what we encountered in 2D. If the particle is pinned, it is restrained from moving in all 3 directions, and we have 3 reaction forces. There is another variation of the pin support not shown here, the so-called ball and socket support. In this support, one end of the member has a ball shape that is embedded in a housing rigidly attached to a wall or floor. The ball permits all rotational degrees of freedom, while the housing prevents the ball from translating in any direction. Accordingly, there are 3 reaction force components. The schematic representation of this looks a little bit similar to a pin. Instead of a triangle in 2D for a pin, what we have for a ball and socket is a housing which is conically shaped, and then there will be we'll typically be able to see the ball, and then the member comes off of the ball at some angle. But we get the same reaction supports for a ball and socket that we do for a pin. As with our 2D illustrations, there will be a special case with ball and socket joints in 3 dimensions. If a bar is supported with such joints at both ends, and there is no intermediate force between the ends, then the bar is reducible to a 2-force member. So generally in something like this, we would have, in some kind of a coordinate system, 3 force components at each end in an x, y, and z direction. We'll call these AX, AY, and AZ, and BX, BY, and BZ. But this will be reducible to something either carrying a tension or a compression if there are no intermediate forces between the ends. So under these conditions, the bar is reducible to a 2-force member with a single force transmitted along the line of action defined by the 2 ball and socket supports. This can be extremely helpful in reducing the complexity of problems. We'll take a look at 2 examples in a minute, one where we can identify a bar as reducible to a 2-force member, and one where we cannot. As in our 2D case, if a particle is located on the rough surface, its motion tangent to the rough surface is impeded rather than prevented. Since roughness is now defined by a plane, we have to allow for 2 reaction components in the plane of the roughness to permit all possible resistance to motion. Finally, for the collar or slider on the frictionless bar, the absence of friction implies no resistance to sliding, so there is no reaction component aligned with the bar. The collar can't be pulled through the bar, however, so there is a normal reaction. But now the locus of all directions normal to the bar is a plane, so we have to include 2 mutually orthogonal reaction components normal to the bar to account for all possible reactions. We now take a look at a couple of 3D particle equilibrium problems. In our first example, we have a mass supported by boom OA and cables AB and AC, and we want to determine the largest mass, m sub d, that may be supported. We know the cables AB and AC have to be in tension and will carry a load along their length. The boom is a bar-like support, and we can see a ball and socket type of support at O. There is no force present between the ends of the boom at O and A, and so this particular element will be represented as a 2-force member and will carry, in this case, a compression that's directed from O towards A. Our interest will be in the end of the boom at A, where we have all of these different elements coming together. So we'll need to begin by drawing a free body diagram of A based on the enveloping surface shown here. We first have the weight of the boom, which I'll represent as the mass of D times G and that will be in the minus k direction. Or we could just write this as minus the scalar magnitude of the weight in the k direction. We're cutting through the boom, and that's going to be in compression, so I'm going to show that in this direction, and we can see that it's directed along the j direction, so I'm going to write the compression in OA is a scalar magnitude to be determined in the j direction. We then have cables going off in two different directions, and I'm going to show those here like this. The orientation of these forces is going to be determined by the geometry of the cables from A to B and from A to C. So I'm going to use unit vectors to describe those orientations. I'm going to write the tension in AC as a vector is the scalar magnitude of that tension to be determined on a unit vector from A to C. And then over here I'll write the tension in AB is a magnitude yet to be determined in AB on a unit vector from A to B. We'll now use the geometry of the figure to define these unit vectors and then define three scalar component equations to solve for the three unknowns, the tension in AB, the tension in AC, and the compression in OA in terms of the weight W. Then we'll separately employ each of the failure criteria that are listed to find the respective failure loads for each individual member. And finally, our limiting mass will be the one that results in the smallest limiting loads for that set of members. The position vector from A to C will be the position vector of C minus the position vector of A. And we can see from the figure that this will end up being minus 8I plus 9k minus 12j meters. The magnitude of RAC will be the square root of the sum of the squares of those components, and that turns out to be 17 meters. So our unit vector in the direction from A to C is that relative position vector divided by its own magnitude, and that turns out to be minus 8 over 17I minus 12 over 17j plus 9 over 17k. Because of the symmetry of the problem, we could do something similar for the unit vector A to B, and the only thing that's going to change here is the sign of the component in the x direction. So if we repeat that process, for AB we get plus 8 over 17I minus 12 over 17j plus 9 over 17k. We're now in a position to write our three scalar component equations. In the x direction we have 8 over 17 TAB minus 8 over 17 TAC is equal to 0. We'll call that equation 1. In the y direction we have minus 12 over 17 TAB minus 12 over 17 TAC plus the compression in OA equals 0. We'll call that equation 2. Finally, in the z direction we have 9 over 17 TAB plus 9 over 17 TAC minus the weight equals 0. We'll call that equation 3. Now, even though we have three equations and three unknowns, this problem is simpler than that because the symmetry of the problem allows us to eliminate one of those unknowns immediately. From equation 1, we can see that TAB and TAC are the same. So if we take advantage of that in equation 3, we get that TAB is equal to TAC is equal to 17 over 18 times the weight. Taking advantage of that in equation 2, we can solve for the compression in OA as 24 over 17 times the tension in one of these cables, which is, again, 17 over 18 times the weight, and that ends up giving us 4/3 of the weight. The fact that this is a positive value tells us that, in fact, the boom is in compression, and so we will use the appropriate failure criteria for that member. For limit loads, AB and AC are the same, and we get that the first limiting weight is 18 over 17 times the allowable tension, which ends up being equal to 4.235 kilonewtons. And on the basis of OA, we have a limiting weight which is 3/4 the allowable compression, which is 5 kilonewtons, and that ends up being 3.75 kilonewtons. So of these two, this is the more limiting value, and our limiting mass then is 3.75 kilonewtons. That's 3.75 times 10 to the third, and a newton again is a kilogram meters per second squared. We're dividing that by the gravitational acceleration of 9.81 meters per second squared. Those unit cancels and we get a value in kilograms equal to 382.3 kilograms. For our second example, we have a bead at C that weighs 10 pounds and is mounted on a frictionless bar AB. We're asked to determine the tension T supported by cord CD and the reaction between bar AB and the bead. The bead C is going to be a subject of interest, and so not surprisingly we're going to draw an isolating surface around that bead, and that's going to be the basis of our free body diagram. But as we do that, there are some complications to this problem which make this more challenging than it might first appear. I'm going to sketch a line of action for bar AB and just represent my bead as a particle like this. We're going to have a weight which will be the scalar magnitude of the weight, in this case in the minus j direction, so I'll write minus W on j. And then we're going to have a tension in the cord, and so we're going to have that tension as the magnitude T we're trying to find on a unit vector that points from C to D. And there's enough information in the figure about the orientation that we're going to be able to determine what that unit vector is. The trickier part now is the representation of the reaction forces between the bead and the rod on which it's mounted. We can't pull the bead through the rod, and so we're going to have normal forces representing those reactions. Again, the bar AB is, or the rod AB is frictionless, so there won't be a reaction parallel to the rod. But the question is, how should we represent those two normal reaction forces? We have an XYZ coordinate system in the figure, but with respect to the reaction forces, we want those parallel and perpendicular to the bar. There are actually infinitely many ways we could represent that, because we could find a continuum of coordinate systems that had an axis along bar AB and then had two other directions that were perpendicular to bar AB. So we have some ambiguity in how we define these things. What I'm going to do is just schematically represent R1 and R2 this way. So here's an R1, and over here is an R2. And we won't say anything more about these yet other than they are both perpendicular to AB, and also they are perpendicular to each other. Now, before we get any further with this, let's also think about what would happen if we were to draw a free body diagram of bar AB. So first of all, we're going to have reaction forces at the point where the bead is mounted that are equal and opposite to the reaction forces that I've shown for the bead. So if R1 and R2 have the directions that I've shown in red above, then the forces that exist on bar AB would be R1 this way and R2 this way. And again, for emphasis, we'll note that R1 and R2 are both perpendicular to AB, and they're perpendicular to each other. Note that the weight of the bead doesn't show up in this free body diagram because that's particular to the bead. As part of the equilibrium of the bead, the weight of the bead will influence R1 and R2, which will then present themselves to the bar AB, but the weight isn't directly present on AB. Notice now that this bar is one where there is an intermediate force between the ends A and B. So even though those two reactions are ball and socket type reactions, we cannot say that the force carried by AB is along the geometry defined by A and B anymore. So if we were going to complete this free body diagram, we would have to draw an AX, an AY, and an AZ here, and we'd have to draw a BX, a BY, and a BZ here. So here is one example where a bar that is ball and socket or pin supported at its two ends does not exhibit the behavior of a two-force member, and we have to have a free body diagram that looks like the one I've shown in green. We will eventually be able to solve problems like this, but this is one where we really have to enforce body as opposed to particle equilibrium, and so we will leave this alone for now. We'll just say that we're going to focus on the bead as a particle. We're going to be able to find the things that we're looking for, and eventually, if we wanted to, we could find the reactions of these ball and socket supports using the techniques that we'll learn about in Chapter 5. For now, though, let's go back to our free body diagram for the bead and see what we can determine about how to solve this problem. I've reproduced the free body diagram from above here, and let's first talk about how we could define solution strategies to find what's requested in the problem statement. A first solution strategy would be to define two directions, we'll call them 1 and 2, orthogonal to AB and to each other. We would then represent the reaction force R as an as yet unknown magnitude R1 on unit vector U1 plus an as yet unknown reaction magnitude R2 on unit vector U2. So here U1 and U2 would now be known, and R1 and R2 would be scalar magnitudes to be determined. We would then solve our 3D scalar equations for magnitudes R1, R2, and the tension in CD, and then reconstruct the reaction force, the net reaction force as R1, U1 plus R2, U2. This is the most direct solution strategy. The downside of this is the first step where we have to define these two directions, 1 and 2. And as I mentioned earlier, there are infinitely many ways to do that, and so you might think about how you would do that, but there'd be a fair amount of work involved in defining what those directions are. This leads us to a second solution strategy, which is to take advantage of the fact that R is by definition perpendicular to AB, to manipulate the vector form of the equilibrium equation to solve for the tension in CD. We would then find the reaction force indirectly by rearranging our vector form of the equilibrium equation to write it as the reaction force is equal to minus the vector tension in CD minus the weight. Now that all sounds very nice, but the question is, how do we do that? First, we'll note from the figure that we can define a unit vector from A to B as the position vector from A to B divided by its own magnitude. We also are going to have the unit vector from C to D from the little icon that shows us the rise over run, defining the orientation of chord CD. So what we'll do is we'll take the dot product between the unit vector AB and the vector form of our equilibrium equation. The vector form of our equilibrium equation is going to be that this sum is equal to 0, and we can further take the dot product between the unit vector AB and each of those terms individually. The first term will give us the scalar tension in CD that we're seeking on the dot product of UAB and the unit vector from C to D. And now here's where there's an advantage to knowing that the reaction force is normal to AB, because then we know from the definition of the dot product that UAB dot R is 0. So there is no second term, or the second term just vanishes, and then the third term becomes minus the scalar weight UAB dotted into J is equal to 0. Then we can find the scalar tension in CD as the ratio of UAB dotted into J over UAB dotted into UCD times the scalar magnitude of the weight. Note that the advantage of this is we don't actually have to define unit vector orientations 1 and 2 like we did in the direct approach. We can get the scalar magnitude of the tension in CD directly, and then we can take that and put it back into this and get the reaction force indirectly from the rearranged form of the vector equilibrium equation. Okay, so the rest of this problem involves carrying out these details. From the figure, we have a rise over run of 12 to 4 and 3, and it turns out if we find the hypotenuse of that, it turns out to be an even 13. So from the cable geometry, we have that the unit vector CD is equal to 3 over 13I plus 12 over 13J minus 4 over 13K. The position vector from A to B is 12I minus 16J plus 15K inches. And again, that's a position vector that has a hypotenuse that works out very nicely. It turns out that if we take the square root of the sum of the squares, the length of AB is 25 inches, and that gives us a unit vector from A to B that is 12 over 25I minus 16 over 25J plus 3 over 5K. So using our expression above for the tension in CD, that's UAB dot J, which would simply be minus 16 over 25 in the numerator. And in the denominator, we have 3 over 13 times 12 over 25 plus 12 over 13 times minus 16 over 25 plus minus 4 over 13 times 3 over 5, and that ratio times 10 pounds. It turns out that this ratio is 0.963, so that gives us that the tension in CD is 9.63 pounds. We can then find our reaction force from the manipulated form of the vector equilibrium equation. So we bring the minus TCD minus W over to the right-hand side. We now have minus 9.63 pounds on the unit vector from C to D. So that's 3 over 13I plus 12 over 13J minus 4 over 13K minus 10 pounds in the minus J direction. When we calculate all that out, we get a reaction force of minus 2.22I plus 1.11J plus 2.96K pounds. In case you were wondering, this is in fact a very high degree of difficulty problem because the two solution approaches are not as clear as they would be in some of our other problems. So we either had to take the initiative to define two orientations normal to bar A, B to begin with, which is the procedure we didn't follow, or we have to recognize that we can sort of back the reaction force out of our vector equilibrium equation by taking the dot product between the unit vector along AB and the vector form of the equilibrium equation to eliminate the reaction force and solve directly for the tension, and then indirectly calculate the reaction force. So if you thought this was a hard problem, it's because it is.